video is going to look at the second in the 3 videos that goes with bonding, and we're going to look at covalent bonding. We're going to look at simple covalent structures, and we're also going to look at giant covalent structures. So what I need you to do is turn to this page here, which says covalent bonding and properties. So the first thing I need you to be aware of is what this word here actually means. So co means to share, so to work together. And valent stands for valency, which is the fancy scientific word for shells. So what we're saying is in covalent structures, they are sharing their shells. Okay, so they're trying to basically get a full outer shell by sharing electrons. So covalent bonding is the bonding of non-metals only. Okay, so when we're talking about that, we're talking about anything on the right-hand side of the periodic table. So carbon, nitrogen, oxygen, fluorine, all of my noble gases, they are all covalent molecules because they're all non-metals. Okay, so when they're on their own, they are non-metals. So what do? So they actually work together, and they do that by sharing. They share their outer electrons. And when I'm talking about outer electrons, I'm talking about electrons on their outer shell. And they share these outer electrons to get full outer shells. Okay? And the bonding here is very, very strong. Okay, so it's important that we are aware that there's a strong bond that it does in fact form. So I'm going to show you how we would draw covalent molecules. And I want to start off by looking at a molecule called ammonia. And there are several molecules you need to know, and I'll tell you them all as we go through. And this is what's in the specification. So that's what the exam board gives us to teach you. So ammonia, you will know from the Haber process if you do triple science. Looks like this. It is called NH3. And I can see I've got my 2 non-metals. So this must be covalent in terms of the bonding that is taking place. Now, I want to show that these guys are going to share electrons in order to get full outer shells. So I'm going to start off with drawing my nitrogen atom. So again, I want to go to my periodic table, and you will see in the video Fundamentals of Chemistry Part 2, we talked about drawing the structure of atoms. So here's nitrogen. I'm going to draw nitrogen in terms of its electron structure. So I can see nitrogen's got 7 electrons. So I'm going to do nitrogen, 2 in the first shell. And then I've got 1, 2, so that's 4, 5, 6, 7. And what I'm hoping you're noticing is I actually draw my electrons like a clock, and that's going to help me figure out where they're going to share electrons. So I can see quite clearly here that actually nitrogen needs 3 electrons to get a full outer shell, because it's got to get to 8. So it's going to get that from hydrogen. And hydrogen, as you can see here, has got 1 electron on its outer shell. So I'm going to draw that separately first so you can see that. Okay. So I can see there is my hydrogen atom. It's got 1 electron on its outer shell, and that's not full. Okay. So it needs another electron. And so what it's going to do is it's going to work together, with the nitrogen in order to gain full outer shells. So I'm going to draw that now. So you can see from its structure, it's got 3 hydrogen atoms. Here I can see there are 3 electrons that needs a partner, needs a pair. So I'm going to show that that's going to share that electron by doing that there like this. Okay. And again, I'm going to have the same here. And then finally, I've got another one there like that. So I can see if I was going to draw that, I would draw that with my nitrogen, okay, in the middle, which is what that middle atom is. And then draw a line to show my hydrogen, because that there is a pair of electrons. So I know that by that line, I've got my pair of electrons. They're sharing those electrons to work together. And again, I've got another pair there. So I've got my hydrogen and another pair there. So I've got that diagram like so. Now, this is what we call our stick diagram. So you can see here, I have got my covalent bond, my non-metals. Each line's a pair of electrons. I've seen exam questions where they give you the bonding diagram like so, and you're expected to draw the diagram. So just be aware that each line is where you have a pair. So if I had two pairs there, like I would have, for example, in oxygen. So I'm going to look at oxygen now. So oxygen, as like most non-metals, is diatomic, so it comes in pairs. And oxygen is in group 6 of the periodic table. So I know it's got 6 electrons in its outer shell. So I'm only going to draw the outer shell in this case today. So here is a typical bonding diagram that they will give you in the exam. And they're very good. They normally give you it, but blank like so. And I know oxygen has 6 electrons in its outer shell because it's in group 6. And I know it needs to get 2 more electrons in order to get a full outer shell. So it's got to share 2 electrons. Each atom's got to share 2. So I'm going to show that by, in that space provided there, I've got 1 oxygen atom sharing 2 of its electrons there. And I've got my other oxygen atom sharing 2 of its electrons there. So I can see I've got in total 4 electrons in that space. So I therefore need another 4 electrons to add to 8. So we'll do the dots first. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So there is my bonding for that oxygen atom. And then I've got 1, 2, 3, 4, 5, 6, 7, 8. And that would be the bonding of oxygen. If I was being asked to draw the actual stick diagram like I've done here, I'm looking for the paired electrons. So I can see there's 2 pairs here. So I'd have my oxygen, 1 line for that pair, 1 line for that pair, drawn like that. And it's got a double bond. So the molecules you are expected to be able to draw are hydrogen, chlorine, remember, diatomic, so comes in pairs, oxygen, nitrogen, water, what else? Methane, and ammonia, which we've already done, which is NH3. And the final one would be hydrogen chloride. Okay, so what I would do is I'd pause the video. I would take a bit of time now to look at trying to draw those diagrams. And then I'll pick a couple and I will show you how to draw those specific diagrams. So I'd pause the video now and then come back and see. So we'll look at drawing, we'll start off with nitrogen. So I can see nitrogen has got 2 atoms of nitrogen. I'm only going to draw the outer shell. So nitrogen has got 5 electrons in its outer shell. I know it's got 2 atoms, so it's going to have this structure, just like we've drawn before. So I'm going to do my 2 circles overlapping, like so, for each nitrogen. Now, the key is working out, well, how many electrons does it need to get to 8? The answer being 3. So that means it needs to share 3 electrons. So in the space where they're sharing, I'm going to do 1, 2, 3 electrons for that nitrogen atom. And I'm going to do 1, 2, 3 electrons for the other nitrogen atom. So in total, I've got 6 electrons here. So this atom's got 6 electrons, so it needs 2 more. And that will make 8 electrons. And again over here, this has got 6 electrons, so it needs 2 more. So each pair of electrons is a bond. So again, here I've got 3 pairs, so that line would be there. I've got my second pair there, and my third pair there, and that is the bonding for nitrogen. Okay, I'll do methane with you now. So methane is made of carbon and hydrogen. So carbon is in group 4, which means it's got 4 electrons on its outer shell. So again, they will give you the structure and you need to be able to put the electrons in. So that's what I'm doing now. Okay, so carbon has got 4 electrons. So it needs 4 to get full outer shell because it's got to get to 8. So I'm going to show the fact that it's sharing 4 electrons. Okay, so it's got 4 electrons there to share. And hydrogen needs to share 1 electron. So there we go. And that there is the bonding of methane, where we've got the carbon, the pair of electrons going to my hydrogen, and there is CH4. Okay, so I would essentially practice it, check it online, check it with your revision guides, but these are the ones you need to be able to draw. So make sure you take the time in order to draw those. Now, we are looking specifically here at being able to draw simple covalent molecules. This is what these are. And you need to know a little bit about them. So the first thing I want to tell you is, not only are you expected to draw the stick diagram where we've drawn, for example, already ammonia, when we drew it like that, you also may be given a diagram that looks like this. These are the mods. These are your 3D models. Okay, and you might be asked to work out the formula from a 3D model or from a stick diagram model like so. So it's important you're able to write the formula for it. So I'll give you a couple of examples just to make sure you're clear on how to do that. So if I gave you a structural diagram that looks like this, what would be its formula? Okay, so pause the video, give it a go, and let's see if you're able to do it. All right, so we've got obviously 2 carbons there. So that means I've got 2 carbons, and in total, I've got 3 hydrogens here and 3 hydrogens there. So I've got 6 hydrogens in total. So it's important you're able to interpret these kinds of diagrams because you are expected to write formulas from them. So it is key that you know exactly how to work out what the formula actually is. Okay, so as I've said, we're going to talk first of all about simple covalent molecules and their properties. So simple covalent molecules. And these are your smaller substances. So your oxygen, your hydrogen, methane, water, ammonia, those molecules we just talked about in the previous page. And you need to be able to tell me a couple of things about simple covalent molecules. One question that does come up a lot is why are simple covalent molecules gases at room temperature? So I'm going to write that down. So why are simple covalent molecules gases at room temp? Okay, so looking at its name, simple, I think not complex, I think weak. So it's the opposite to giant. So just keep that in the back of your minds. So to break that answer down, it's usually a 3 marker, could be a 4 marker, it just depends on what the question is asking. Key things you need to say is, first of all, is that we've got covalent molecules, okay, and these are simple in terms of their structure. They have what we call weak intermolecular forces, and I'll draw a picture of what that means just to explain that to you. So let's imagine I've got chlorine gas, which is Cl2, and here is chlorine attached to another chlorine, okay, and chlorine attached to another chlorine, if I can draw them attached. Now, within that chlorine atom, these two atoms here, that bond is very strong, okay? But between these molecules, okay, that there is what we'd call a weak intermolecular force. So in other words, it's the force between the molecules that is weak. So when I come to heat up the substance, these forces are easily overcome, which is why they're usually gases at room temperature. So covalent molecules are simple in terms of their structure. They have weak intermolecular forces, so therefore have low melting or boiling points. So you need less energy to overcome these forces. So less energy is needed to break the intermolecular forces. And so as a result, they can part quite easily, and that is why simple covalent molecules are generally gases at room temperature. Okay? They do not conduct electricity. And the reason being is you don't have any ions involved here, and you don't have any delocalized electrons involved here. So therefore, it doesn't, in fact, conduct electricity. So you do need to know that. They are usually gases. They can also be liquids. So water, for example, at room temperature. And we know why. They have these weak intermolecular forces, which makes them have a low melting and boiling point, so less energy is needed to part the molecules. So therefore, that's why they've got a low melting and boiling point. As what I will say though is, as the molecules get bigger, okay, so the size of the molecules gets bigger. So as the molecules get bigger, so for example, hydrogen, H2, compared to say methane, that's a much larger structure. As the molecules get bigger, the intermolecular forces increases. Okay, and that means you need more energy, which is why they generally, the boiling point and melting point increases. So as the molecules or atoms get bigger, that means that there's a bigger force or bigger intermolecular force of attraction. So therefore you need more energy, and which is why they've got a high melting and boiling point. Okay, so that's simple covalent molecules. What I do want to do though is jump now to giant covalent structures. Before I do that though, I want you to see there's a blank page, and there's a blank page in your booklet for a reason, and it's just after metallic bonding, because you need to be aware of something called polymers. And it's important you know that polymers are covalent structures. So that means they are made of non-metals, and we normally talk about polymers when we come to look at alkanes, alkenes, cracking, making polymers in paper 2. But you need to know about polymers in terms of their structure, the fact that they're covalent, the fact that they are non-metals. You need to know a little bit about what a polymer looks like. So I'll draw what a polymer looks like. So polymers will often have brackets, and then you will find something that looks a little like this. Okay, so this is a diagram of a polymer, and it has got this structure here. So I just want to make you aware it's got brackets. This means many. Okay, so basically a large number of what's inside this bracket. And that there is the repeating unit, which we know is actually a monomer, okay, because monomers join together to make polymers, okay, so that would be the repeating unit. But you might be asked to identify a polymer. You're looking for the brackets, you're looking for this little n, and that will tell you that it is indeed a polymer. So polymers have usually got the word poly at the start of their name. So polythene, so polythene, which is what makes your plastic bags. Okay, it's made of ethene, which you'll know in paper 2 looks like that. Okay, because double E means double bond, so that is my monomer. And then when it forms the polymer, it actually breaks that double bond down with the H's, like so. And then I've got my polythene, so long chain there. The intermolecular forces, which we've talked about already, between the atoms is strong. Okay, so the intermolecular forces, molecular, oh my goodness, can't spell at all, intermolecular forces between the polar molecules are large. Okay, they're larger than the simple covalent. So intermolecular forces are larger because the molecules are bigger. And we've already explained that in the last page in the booklet. So intermolecular forces are larger. That means that there is a stronger intermolecular force. Okay, so that means you need more energy needed to therefore melt or boil the substance, which is why they're usually solids at room temperature. Okay, so bigger molecule, because it's bigger, it's got more intermolecular forces. So therefore you need more energy in order to break those forces, which means that polymers are generally solids at room temperature, and which is why they have a higher melting and boiling point when compared to simple covalent molecules. What they do, however, have are lower, so they do have lower melting and boiling points compared to, say, ionic, metallic, and your giant covalent structures. So just be aware that we've got big structures that are polymers. They're made up of repeating units. They look like this. They have the brackets with the N. The N means many. And this is covalent bonding because I've got non-metals bonding together, sharing electrons in their outer shells. And the name of a polymer usually always begins with poly, and then the second part of the name is usually the monomer. So in this case, we've got ethene, monomer, the double bond breaks, and then we form this big long chain polymer. Because the chain is long, it means you've got more atoms, so the molecule is bigger, and you know that means that the intermolecular forces will therefore increase. So anytime that happens, we need more energy to overcome those forces, which is why they're solids at room temperature, and it's usually why they have a higher melting and boiling point when compared to simple covalent, but they still have lower melting and boiling points when compared to the other types of bonding. So the last little part we're going to look at in terms of covalent structures are our giant covalent structures. And there are 3 that you need to be aware of. So again, I'm going to use the word giant. And when you think giant, you think strong bonds and you think high melting and boiling points. So these are giant structures. And as I've just said, there are 3 that you need to be aware of. So this is graphite, diamond, and silicon dioxide. So these are the three giant covalent structures that you need to be aware of. You need to be able to describe the structure and then link the structure to the properties. So we'll start with graphite. So this here is graphite, and graphite is made of carbon. And what's really unique about graphite is that it is a non-metal because it's made of carbon, but it's a non-metal that can conduct electricity. And there's a reason for that. If you look at the diagram, can you see how each atom forms 3 bonds? Now, in reality, carbon is in group 4, so should therefore form 4 bonds. So we have a carbon molecule that has 3 carbon bonds, which leaves behind this delocalized electron. And we know delocalized means free to move. And so the graphite molecule, the giant structure, can conduct electricity because its carbon atoms has 3 carbon bonds when it should have 4. And as such, it's got a delocalized electron, which is free to move through the structure. And that's why graphite can conduct. Now, graphite does come up in electrolysis as well, so just be careful, it could link to electrolysis. The second thing you need to know about graphite is that it is soft and slippy, okay? And you need to be able to link that to its structure. So what I hope you can see from my picture is that you've got these layers. And we know from metallic bonding that layers generally can slide. And if layers can slide, that means they are usually soft and slippy. So it's important you're able to explain why graphite is soft and slippy. So it's soft and slippy because the structure is arranged in layers. There's a weak intermolecular attraction between each layer. And as a result, those layers can slide, which makes graphite soft and slippy. Okay. What other structure you need to know? So here is silicon dioxide. Okay. So di means 2. So you can see from my diagram, I've got a silicon molecule attached to 2 oxygen molecules there. And again, this is a giant structure. Silicon dioxide is also known as silica. All you Minecraft fans will know that silica is in fact sand. And 1 grain of sand is 1 giant structure like this, which is kind of cool when you think about it. But it's a giant structure, so we know giant means you've got strong bonds. Okay, so strong bonds, which means you then need lots of energy to overcome the force, which is why they have high melting and boiling points. And that's the same for graphite. Graphite also has high melting and boiling points because it's got those strong bonds. Okay, and then the final structure you need to be aware of is diamond. Okay, so here is diamond, again made from carbon. Okay, it's a giant structure. And as you can see from the picture, each carbon forms, well, pretty much can see from the picture, each carbon forms 4 bonds. Okay, it is a very rigid structure. And again, you need to know that as a result, it's got strong covalent bonds. So therefore, we need lots of energy to overcome those bonds. And that is why they have a high melting point and boiling point. Okay, so diamond and the silicon dioxide do not conduct electricity. So it's important that you know they do not conduct. But graphite does, and the reason why is because of the 3 carbon bond when it should have 4. So it's got delocalized electrons that are free to move through the structure, and this is why it can conduct. So that's your 3 giant covalent structures that you need to be aware of. Again, they're all covalent because they've all got non-metals, but in this case, they are giant structures. Okay, just to point out, diamonds are also really hard, and that's down to the complexity of the bonding. Now, the final things I want to talk to you about in this video are what we call, fancy word, allotropes of carbon. And basically, this is different forms of carbon that can exist, and as a result, it changes the properties of the carbon. So graphite is one of them. So we know graphite is a structure, a giant covalent structure that is made of hexagons that form these layers. And between the layers, we have these, I'm going to go back to the picture just to show you. So here is my hexagon structures that form these layers. Between these layers, these are weak bonds, but as I said, that's what allows it to slide, which is why it's soft and slippery. It's often why graphite can be used as a lubricating material. So just be aware of that. But it is a giant structure, which is why it's got high melting point and boiling point. So lots of strong covalent bonds, lots of energy needed. And we know why it can conduct electricity, and this is also the reason why it can conduct thermal energy, heat. But we can also have variations of that specific type of molecule, and that is where we come to our allotropes. And this here is something called graphene, which is essentially one layer of graphite. So what we're saying there is it's like one atom thick, and as a result it makes a 2D structure. So it's like essentially one layer of the graphite structure. It's got this network of covalent bonds. So again, we've got these strong covalent bonds. Okay, but what makes this really unique is it's in fact very light because it's down to it being one layer. So it's often used as what we call a composite material. And we talk about composites in paper too, but composite material that basically is used to improve the strength of other materials, for example. And as it's a one layer of graphite, it has those 3 carbon bonds that we've talked about already. So has the delocalized electrons that are free to move. And this is why we often find graphene in the computing industry. Okay, so it's usually used in electronics because it's light, so therefore easily positioned. It's can conduct electricity, so it's a really useful material to be used in electronics. And then the final allotrope you need to be aware of is these things here, which are called fullerenes. And you sometimes see them like this. You might see them as like tubes. I wish I could draw, but they might appear like tubes like so. Okay, so just be aware they are all fullerenes. And fullerenes are generally, they're made of carbon. This is why they're allotropes of carbon. And they are usually shaped like closed tubes, as you can see here. Or they are hollow balls, like this molecule here. This molecule is called, you'll never believe the name of this. This molecule is called the Buckminster fullerene. So they're called buckyballs. So Buckminster fullerene. And it was actually the very first fullerene to be discovered. and it's got the structure C60, so it's made of 60 carbon atoms. I'm sorry guys, you need to know that. You need to know that number. I have seen questions, ticky box questions in particular, where you need to be able to identify this. So it's a hollow structure. And the reason why it's a hollow structure, and again here I've got a hollow structure too, so just be aware of that, is because actually these are usually used to what we call cage, okay, other molecules. So they act like a cage to trap in other molecules. And that's why they're often used in the delivery of drugs in the human body, because these are exceptionally small in terms of size. So just be aware they're small. They might look big here, but they're actually quite small structures. And because they've got a cage structure, the drug, for example, can fit inside that cage and it can then deliver a drug within the body. They have high surface areas. Okay, so huge surface area. And this is why they're usually used as catalysts as well in industry. And we know from paper 2 that catalysts speed up chemical reactions. And obviously we've got a tube shape here, which means they can also be used as lubricants because they can slide due to the shape. And you also need to be aware that actually we have these carbon atoms arranged in hexagons, pentagons, heptagons, and sometimes you get a maths question around that. So just be aware that hexagon, pentagon, heptagon, what does that actually mean in terms of numbers? Okay. These are also examples of what we call nanotubes. Okay, so nanoparticles, so nanotubes, nanoparticles. I do want to point out that nanotubes and nanoparticles is only on triple science. It's not on the combined science route. So just be aware of that. But nanotubes are tiny, very tiny molecules. They've got a high ratio of length to diameter, and they're very good at conducting electricity and heat. They've got a strong tensile strength, and it's often why they're used in electronics and in industry, nanotechnology. So that there is your allotropes of carbon. That is your bonding, your covalent bonding, the bonding of non-metals. So as you can see, it breaks down into our simple covalent structures, our giant covalent structures, the 3 that you need to be aware of, and then our unique structures, which are our allotropes of carbon. So hopefully you found that useful. Any questions, please just ask me when I see you in lesson, and I will leave it there. Thank you.